All right. This is Physics 1C for May 3rd, or June 3rd, and today we're going to be finishing up our discussion of electromagnetic waves. So just to kind of cover something we did last time. Last time we were talking about plane electromagnetic waves, and a plane electromagnetic wave would be a wave where successive wavefronts are basically parallel to each other. And all along one plane you've got different values of electric and magnetic fields, and we're imagining that there's a wave that's propagating, and it looks something like this, where the electric field propagates and looks like the the XZ plane in this picture, and the YZ plane you have the magnetic field propagating. And we used this last time to sketch out and solve Faraday's law by calculating this loop integral, this path integral, around this yellow path right here, and that led us to this from last time. So we're going to take what we learned last time, we're going to need that for today, and we're going to continue to use Ampere's law on this same setup. So here's the same setup we had from last time. And let's just zoom back in a little bit more. So this is the result we got last time. This is the result that came, remember, directly from Faraday's law, so I'll just write that down. So this is pretty much Faraday's law as it applies to our system. Okay, and so now what we'd like to do is to use Ampere's law on our system. So this was the system we had from before, and the path that we used was this. But now I'll remove this because we're going to do a new path to use Ampere's law. And remember that the whole goal of this is to prove that there is such a thing as an electromagnetic wave, and to basically calculate the speed at which it propagates. So let's go ahead and continue. So now what we need to do is we need to draw a path integral so that we can evaluate this quantity, the integral of v dot dl. And Faraday's law states that this should be equal to like I said, Ampere's law says this. And we're doing this in free space. We're looking at the solutions for Maxwell's equations in free space, which means that we're not going to have any electric charges and no electric currents. So normally you'd have another term in Ampere's law that would look like this. But we're going to say that there are no currents in this region, so we're going to make that term equal to 0. So we just need to calculate each of these quantities right here. So let's start with the one on the left, the integral of b dot dl. In order to calculate that, we're going to have to draw a loop on our picture right here. So let's go ahead and do that. The loop that we're going to draw is going to kind of come, I'm going to draw along the bottom edge down here, like this. So that's going to be one side of it. Copy, paste. Here's the other side. We'll get them to line up here in a second. And then we need another line that connects the two of them. There we go. And we're going to go about this path. So this is our path. Which direction are we going to go? We want to go in such a way that the electric field is pointing up for our path, right? So that would be this way, I think. I'll draw it and I'll tell you why I picked that direction. Okay, so the direction of the electric fields, as we move from plane to plane here, is pointing up, right? So what I'm doing is I'm basically using my right-hand rule to determine the direction of the path here. So I'm taking my thumb and pointing it in the direction of the electric field, which is up, and then using my fingers to sweep around the direction that I want to use the path. The reason for that is because then when we calculate the flux will be positive, and when we calculate the magnetic field, we'll get what we get from here. Okay, so that's going to be our path. Now, it's kind of hard to see this, so we're going to draw a two-dimensional version of this path here, just like we did last time. This path is drawn into, so this is the z-axis right here. This is the x-axis, so the path is in the xz plane. And yeah, so let's draw another picture of it. This is the positive z direction over here, right? So what we're going to do is we're going to draw a coordinate system. I don't know if it's going to let me do this, will it? No. Maybe I can flip it upside down if I do this. No. Let me invert. I want to flip vertical. There we go. Okay, because I want the positive z-axis to be going down and the positive x-axis going to the right. So this is going to be the plus x-axis. This is going to be the plus z-axis. And I don't know if I can shift this into the positive area. I think I can, maybe, to make what I'm doing a little more clear. If I put this over here, that's still pretty clear, right? Okay. All right, I haven't really changed anything. I've just drawn the two planes into the positive x plane so that what I'm about to draw will be consistent. All right, so I think we're still using delta x for the size of our path here, so that stays the same. That's what that says. Here, let me move that back and then just show that there's the delta x. Let me move it down far enough. What if I move it over here, and I take this and just get it out of the way? That'll be a little more clear, right? And then we just put this somewhere like right here. And then just say now delta x is this distance. There we go. Okay. All right, so this is the xz plane. And on this plane, we're going to need to draw a magnetic field vector that's pointing this way, and a magnetic field vector... Oh, our magnetic fields are going this way, right? Okay, so this way and this way. So let's draw our path on here. We'll start with that. That's the easiest part. Our path is just going to be a box. And on the right side of our path, we're going to have a magnetic field vector that's pointing this way. So down. Let's see. Our path points this, 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 this. This is the path for the integral. We're going to put the magnetic field vector in here. We're using dark blue. Okay. So we draw one magnetic field vector like here. And we do the same thing over here. The idea with these is that these magnetic fields are going to be slightly different from one another. So we'll give them different names. Let's just make this one shorter, I guess. We're going to call the one on the left B1. One on the right we're going to call B2. And we're going to say that the x-coordinate right here is going to be just x. And then this is delta x from here to here. And we also need the other, the other dimension of our path, which is going to be a. So that's going to go from here to here. I think we're good. The last piece I guess we need to throw in here is we're going to say that the electric field in this region is coming... Well, maybe I should stop and have you guys tell me instead of me drawing everything so that you can have a chance to actually think about what's going on. So I've drawn the magnetic fields down in the positive z direction. What direction should I draw the electric field here? Should it go into the page or out of the page?
Out.
Out of the page, I agree. And we're going to do the same thing we did last time where we're just going to average the electric field over this region. And we'll just call it E. We need a vector, right? And we'll just say in this case that E basically represents the average electric field in this region between these two positions, okay? I think then we have everything that we need. So let's calculate what integral b dot dl is going to be here. So if we do the integral of b dot dl along our path, then we need to draw our dl's in here. So like on the bottom, dl is going to go this way. On this side, dl is going to point this way. On the top, it goes that way. On this side, it goes this way. Let's start on the left side. So on the left, we have b1 dl, which is just going to become b1 times this length a, On the bottom, their magnetic field would be pointing downwards, but DL is going to the right, so we get 0. On the right-hand side, we have B2 going down and DL going up. So we're going to get negative B2 DL. Not DL, sorry. Negative B2 times this length here, which is A. And then along the top side, we'll also get 0. So all told, we get B1 minus B2 multiplied by A. Now, the way that we'll rewrite these is to say the following. So we're going to call B1 the z component of B at the coordinates of x and time t. And we're going to write B2 to be equal to BZ at the coordinate of, so this is at this point right here, we're at the coordinate x plus delta x, so we put x plus delta x in here. And we'll plug those into our equation now. So now we're going to get that integral of b dot dl is equal to, so we have b1 is bz of x and t, just the z component of the magnetic field at coordinate x and time t, and then we have minus bz of x plus delta x, comma t. And all of this is multiplied by A. And that's all we can really do with that one for now. Any questions about what we just did? All right. Next thing we're going to do is say, okay, the electric field here is pointing in the positive y direction on our graph. So x, y, and z. Y is up. Electric field's up. So we're going to call this the y component of the electric field here. And we're going to say that when we calculate our flux, the electric flux, since we're averaging the electric field over this region, all we have to write is EY multiplied by the area of our box, which is A times delta X. And that should give us our flux. And then we just need to put them together using Ampere's law. So Ampere's law tells us that if we write integral of b dot dl, that this is equal to the mu naught epsilon naught times the time derivative of phi e dt, time derivative of the flux. And on the left-hand side of our equation now, we're just going to put this in here. We can just copy-paste it. And on the right-hand side of your equation, we're going to have mu naught epsilon naught ddt of EY. This is multiplied by, sorry, this is kind of confusing the way that I wrote this. This is multiplied by A times delta X. A and delta X are going to be constants, so they're not going to take part in this, this equation right here. And this EY, when I'm writing it, is also a function of X and T. Okay, now what we can do is we can cancel out the A's from both sides. And what we're going to have is this. I'm going to rearrange these to get this second term first. So I'm going to write it like this. So I'm going to basically factor a negative sign out of the left side like this. So this is the same as this, right? Negative on this one, negative, negative. This one's positive. And we're going to divide this one by delta X. And then this is all equal to mu naught epsilon naught ddt of the y component of the electric field evaluated at X and T. Okay. And the next thing we do, like we did last time, is we're going to take the limit as delta X approaches 0. And then the left-hand side here is then going to become a partial derivative. And the right-hand side is just going to be mu naught epsilon naught. There's a negative sign, because there's a negative sign here. And then ddt of the function ey. There we go. So this is what we got from Ampere's law. And according to what I've been saying for the last week or so, if we combine these two together, hopefully we're going to produce a wave equation. That was kind of the goal of all of this, was that if we could combine together Faraday's law and Ampere's law, that it's going to create some kind of a differential equation that we hope looks like a wave equation. So we need to combine these two together. And just to remind you the kind of what the wave equation looks like, we're trying to make it so that when we take the second derivative of our function with respect to x, that it's equal to 1 over the velocity of the function, the velocity of the wave squared, times the second derivative of the function with respect to time. So we'd like to be able to get something into this form where instead of y, we have b and e, pretty much. So let's see if we can do that. We can see from the form of this equation that we need to get second derivatives, but from Ampere's law and Faraday's law, we only have first derivatives here, right? So in order to deal with that, what we could do is we could basically, let's say, for example, on Faraday's law to the right, if we took the time derivative of both sides, then we would get something that had something to do with the second derivative with respect to time here, right? If I take the time derivative of both sides of this, then the right-hand side is going to become the second derivative with respect to time. And we're going to do something similar over here, but we're going to do the spatial derivative. So for the left equation right here, we're going to do del x of the whole equation of the whole equation. So we're going to have to do like this. And what we'll get on the left-hand side is negative second derivative of bz with respect to space. On the right-hand side, what we'll get is like a mixed partial derivative, where it's going to be the second derivative, but it's the derivative of x and then t of ey. All right. And then we'll do the same thing over here with Faraday's law. We're going to take the time derivative of both sides of this one. I was confused for a second as to whether or not that negative sign should be there, but it's right, because Faraday's law has a negative sign in it. Okay, left-hand side of our equation now is going to become del 2ey, again, another mixed partial, del t del x equal to negative second derivative of bz with respect to time. So now we have this situation where we have this term here that shows up kind of twice, because I'm sure this is something you learn in your Calc 3 class, right? That if you have a mixed partial like this, it doesn't matter which order you do the derivatives in.
That's true.
Yeah.
Is that always true?
As long as it is that the derivatives are like defined, I think, individually at that point.
Okay, so if one of the derivatives were to give you infinity or something like that, or whatever, or if it was like
then it gets wonky.
Piecewise function, or it had like corners or something. Okay, so these two terms are equal to each other, basically, right? So what we can do is we can just take this piece, the mu naught epsilon naught, and let's divide it to the left-hand side over here. So this says now use the same color. This is now going to say 1 over mu naught epsilon naught times this is equal to this. And then what we can do is we can just make them all equal to each other. And what we end up getting on the left-hand side over here is 1 over mu naught epsilon naught. There's a negative sign. Del 2 bz del x2 is equal to negative del 2 bz del t2. We get rid of the negative signs. We're going to move the mu naught epsilon naught back to the right-hand side now so that it looks like this. Del 2 bz del x2 equals mu naught epsilon naught times and this, if we compare it to our wave equation up here, which is slightly off page, this shows that the function bz should satisfy the wave equation. The z component of the magnetic field should satisfy this traveling wave equation, as long as this term represents 1 over v squared. So that means that mu naught times epsilon naught has to be equal to 1 over the velocity squared for our wave, which means that we can calculate the velocity of the wave as 1 over the square root of mu naught times epsilon naught. And if you plug in the values of mu naught and epsilon naught into this equation, I think we did this at one point in this class, what you're going to get as your answer here is about 3 times 10 to the 8 meters per second, which is also known as the speed of light. And presumably, at some point in time, Maxwell did this calculation and realized that this means that light basically has to be an electromagnetic wave. It has to be a wave that's composed of electric and magnetic fields. And now we know that this is true, and all forms of light, whether it be visible light, infrared light, ultraviolet, radio waves, all of those types of light, all those types of electromagnetic radiation travel at the speed of light. And it also shows us that the speed of light is related to these two quantities. It's related to mu naught and epsilon naught. It's related to magnetism and electricity, right? It's a good idea at this point to talk about what these quantities represent. So mu naught is basically the resistance of space to setting up magnetic fields, and epsilon naught is basically the resistance of free space to setting up electric fields. So it's kind of like, how hard is it to produce a magnetic or an electric field in space? That's what these things represent. And so it kind of makes sense in a way that the speed of light has something to do with that, especially because if light is something that's related to electric and magnetic fields that are basically oscillating through space and time, then the speed that it can propagate at is going to be dependent upon how much space resists your attempt to put one of these fields into place. But this is a really remarkable result that the magnetic field here satisfies the wave equation. That means that Bz of x and t is going to be a traveling wave. And we're going to talk about specific solutions to this, but we've already seen that there's one particular solution where you basically take the function Bz, needs to have x minus Vt in it. So we'll look at that. We're specifically going to talk about sinusoidal waves today, though. But yeah. It's also important to understand that the electric field is also going to satisfy the exact same equation. I'll leave this to, you can prove for yourself if you want to. But the way that I did this ended up making it so that our final result had Bz in it. But if I switch these derivatives, if I did time on this side and space on this side, then our final answer would have had Ey in here. It would have been the exact same equation. Exactly the same equation. So that also means that the y component of the electric field in this case is also going to represent a traveling wave, a wave that's traveling through space at the speed of light. And that's a pretty remarkable result. That just from Maxwell's equations, this is now why we call these Maxwell's equations. This is because he basically solved them, right? He took the last two, Faraday's law and Ampere's law, he pushed them together and proved that you get traveling waves that travel at the speed of light which proves that electricity, magnetism, and light are all different aspects of the same physical phenomenon. And that is, I think, pretty remarkable. You have any questions? The path direction? Sure. So when you're doing a path integral, right? In this case, this is going to be a closed path. So we have to choose when we go around our path right here to either go as we did, which is counterclockwise, or we could go clockwise, right? It turns out that it doesn't matter which one we do, but the one that I chose avoided putting a bunch of unnecessary negative signs in. So this path, when we calculated the flux, one thing I left off of here is that our area vector in this case, oh, that's not what I meant to do. Our area vector in this case, oh, come on, please. I have to click this off, I guess. Come on. What do I select? There we go. Really? It's still selected? How do you deselect these things? There we go. All right, so the area A, or we usually use dA, comes out of the screen. So when we calculated the flux, we got a positive number, right? Because the flux is E dot dA, and if E is out and dA is out, then you get just a positive number. So then what I said was, since I want to get a positive value for the flux, I'm going to use the direction of my path to correspond to that. So if I put my thumb in the direction of the electric field, which is out of the page like this, and then I swing my fingers around like this, then that's going to tell me the path direction, the direction that my right hand rotates. And that way, when we did this calculation right here, we ended up getting this. This one had a negative sign and this one didn't. Had I chosen the other path, the only difference would be that the negative sign would have showed up over here. But it'd still be the same equation, right? Does that make sense, Henry? Okay. It's not super important, but it is important when you're trying to understand certain things. Okay, so we have these traveling waves. Any other questions or comments about this? You know, one thing that I did not talk about that I probably should have, and how much do you all know about the spectrum of light? The electromagnetic spectrum. I didn't talk about this at all, and it's definitely going to be relevant for what we're going to talk about next.
There's different types of light, right? Like infrared, UV, visible light.
Yeah.
Visible light's pretty small pretty small compared to what humans kind of say is the spectrum.
Yeah. So this is the electromagnetic spectrum. It's composed of radio waves. IR stands for infrared, which means below red. UV stands for ultraviolet, which stands for above violet. And what is below and above? Well, it's a wavelength. So it's actually frequency, right? Ultraviolet is frequency, yeah. Ultraviolet is higher frequency. Yeah, blue is higher frequency. Red is lower frequency, right? Okay. So the ultraviolet means it has a higher frequency than violet light over here on the left. The infrared means it has a lower frequency than red light over here on the right. In case any of you don't know about this, which one? I think it was UV light. UV light was first discovered by, oh man, I can't remember his name right now. But there's actually an experiment you can do that's really interesting where, yeah, I think you can do this at your home
Ritter?
too. What's up?
Johann Ritter?
Is that who it was? Let me tell you the experiment. You tell me if this is the same thing. You can basically take a thermometer and you can place it down onto like a piece of paper, basically. So like, let's say you take a piece of paper, right? And you draw like violet, you draw just different colors. That's not how we did it. No, you do it with a prism, right? So you take a prism, it takes white light from the sun, and it spreads it out into basically a spectrum, something like this. And one experiment you can do is you can put a thermometer down next to the violet light. You can put a thermometer down next to the the blue light, the green light, et cetera, et cetera, et cetera. And you can see that the temperature of each of these colors of light is actually different.
That's a
And
smart idea.
it's pretty smart, yeah. And what he noticed was that if you put a temperature to the left of the violet light, that it's even higher than the violet light, which is evidence that there is some type of light that's being produced that has a higher amount of energy than the violet light, a higher amount of temperature than the violet light, but we can't see it. It's invisible to us, right? And so that's why we call this visible light. We can only see this tiny little spectrum right here, but we can detect the other ones, right? And so I think that was the first time anyone detected UV light. Nowadays, you can produce ultraviolet light by, you can go and buy things at novelty stores, like black lights and stuff like that, that produce ultraviolet light. And we're pretty comfortable with the expression ultraviolet light because I think something that a lot of people know, especially here in California, is that you get sunburns from ultraviolet light, right? So it's a good idea to have sunscreen that can protect you from this. As you go farther up on the spectrum, you get things like Xrays. Everyone's heard of Xrays. You can go to the doctor to use Xrays as a way to have a form of light that can penetrate your skin and give you a vision of your skeleton. And then gamma rays are an even higher energy type of X-ray that are produced. These are usually produced by high energy rays coming from space. And X-rays also come from space. Things like, I might probably get this wrong, but I think it's like some black holes and some quasars produce X-rays. As we go lower on the spectrum, we get radio waves. We use radio waves extensively to communicate here on Earth, both through old school like AM, FM radios up to modern like Wi-Fi communication devices. We still use IR for television. This is a pretty new TV I have. It's probably like 1 or 2 years old or something like that, and it still uses an IR device. An IR device looks something like this. When you have, I don't know if you can see this very well on the screen, but the little, when you have like a little light bulb, I guess you could say, in the top of your remote, that sends an IR signal that's picked up by your TV or whatever device you're using. So yeah, all of these things are light, or more properly, electromagnetic radiation. And the thing that characterizes the different types are their wavelengths. Okay? You can find all sorts of different pictures of these things that give you different information about them. For example, this one gives you like a little picture. Like for radio waves, you've got this. Obviously, you've got like your Wi-Fi signals and your phones and I guess your TVs. And then you've got your visible light. As Cam said, though, something that's really important to understand about this is that the visible light spectrum is extremely tiny. Okay, the spectrum of electromagnetic radiation goes from a frequency of 10 to the 0 up to 10 to the 26, but the frequencies of visible light are just this 10 to the 14 band, between 10 to the 14, and well, that's pretty much it. Okay. All right. Oh, you also get gamma rays from particle radiation. I kind of left that part out. And here's like a tanning bed for the UV light, right? So you can find all sorts of different animations and descriptions of these electromagnetic phenomena. And some of the things that we're going to want to describe about them when we're talking about these light waves is any wave. I'll draw a little picture right here. So we got a wave. And any wave has the following properties. It has something that's called a wavelength. The wavelength is the distance that you need to travel along the wave before the wave starts to repeat itself, right? So a wave of any kind is going to tend to repeat itself, right? Like this. And so one wavelength can correspond to the distance from this point to this point, or it could be the distance from this point to this point. Doesn't matter, it's just the distance that you need to travel along the wave until the cycle repeats. And wavelength is related to frequency through an equation that's called this. So you take the speed of light is going to be equal to the wavelength of the wave multiplied by the frequency. We also use and wavelength is measured in meters, frequency is measured in hertz. We also use other symbols for these as well. So there's something that's called the wave number. I think probably a lot of you have heard of wavelength and frequency. You may not have heard of wave number. So wave number is defined as K. This is used a lot in physics textbooks. K is equal to 2 pi divided by lambda. So it's going to have the units of like radians per meter. Those are the units of this. The other thing that we define, and we've seen this before, is the angular frequency, where instead of frequency, which is measured in hertz, we have omega, and omega is equal to 2 pi times the frequency, and this has units of radians per second. And when we combine them together, if we write c equal to omega divided by k, you're also going to have an expression for the speed of light as well. Does that work out okay? If you combine these two together? Put k in the denominator because then the wavelength goes to the numerator, the 2 pi's cancel, and these two equations are basically the same. So 2 different ways to describe the properties of a wave, either using wavelength or wave number, frequency or angular frequency. For what we're going to talk about next, we're going to be using omega and k, so I figured I'd write those down. All right. Does anyone have any questions? So the next thing to do is to talk about sinusoidal electromagnetic waves. How are we doing on time? We're fine. Okay, so the wave equation, as we have it up here, in Physics 1b, we look at one of the solutions of this wave equation that looks something like this. You take the amplitude of your wave and you multiply by the cosine of kx minus omega t. This function will also satisfy the wave equation, and you can prove it for yourself. It looks a little different from the kind of functions we were using last time. Last time we were looking at functions that look something like this. Y of x and t was equal to something like a times the cosine of x minus vt. We didn't specifically look at this one, but I just said any function that has this form, where this is the kind of, I think you call this the argument of the function, this will automatically satisfy the wave equation. Turns out that this will as well, and you can prove it yourself by, well, how do you do it? Well, you take the second derivative with respect to space, you set it equal to 1 over v squared times the second derivative with respect to time, and things will work out, mostly because when you take the second derivative with respect to space right here, you're going to get a k squared, right? When you take the second derivative with respect to time, you're going to get an omega squared, and then they'll show up in just the right way, that those will be the speed of the wave that'll show up just like this. So this also satisfies the wave equation, and gives you the wave number and the angular frequency as well inside of it, okay? Okay, so we're going to apply this same solution, or this type of a solution, to our electromagnetic waves. So we knew that Ey of x and t had to satisfy the wave equation, so we can basically just say, let's replace the amplitude here with just the maximum value of Ey. I'll call it Ey max. And we multiply that by the cosine of, I don't really need to call it Ey max. Let's just call it E max. I think that's confusing if I call it Ey max. So we'll just call this E max cosine of kx minus omega t. And for bz, what we'll have is bz of x and t is going to be b max multiplied by also the cosine of kx minus omega t. And these are going to be our electromagnetic and magnetic fields. But we know that electric fields are vectors, so we can write this in a vector equation like this. If we do j hat multiplied by E max cos omega t, or kx minus omega t, and we do b is equal to, so this is pointing in the z direction, so this is going to have to be positive k hat, b max cosine of kx minus omega t. Okay. So, one piece that I've kind of left out of all of this is that the speed of these waves, c, is going to be equal to the ratio of the magnetic and the electric fields. I've left this out. This is one of the things I noticed when I was going back through the notes that I forgot to say, but the speed of light c is equal to this ratio. If you'll remember, we go back way back into the chapter on magnetism, when we first talked about it, we talked about this thing called a velocity selector, and we realized that the ratio of the electric field divided by the magnetic field gives you velocity. So that's part of where that comes from. Okay, so the other thing that we can say about this is that the direction of the wave is going to be given by E cross B. So in this case, because E is in the j hat direction and B is in the k hat direction, what direction does this wave go? We would have, yeah, you do j cross
the I hat, yeah.
Yeah, j cross k, which is the positive I hat direction. Okay, so these two equations represent a wave that's traveling the positive x direction, right? What could I change for either of these if I wanted to make it travel in the negative x direction?
You could just smack a minus sign
Yeah.
on one of them.
On one of them. We can't put it on both of them, because if we put a minus sign on both of them, it's still going to be traveling the positive x direction. If I make this one negative, then now what we'd be doing is negative j hat times, obviously this is the negative I hat direction, right? So that's how if in some of your problems, you're going to need to use that information to solve. I think probably in the very next problem that we're going to do. All right, that's all we need to say about it. So let's do a problem. We'll probably do this problem and then take a break. All right. So we have a carbon dioxide laser emits a sinusoidal electromagnetic wave that travels in vacuum in the negative x direction. So that's shown in this picture right here. Magnetic field's up, electric field's this way. The E field's oscillating in the z plane. The magnetic field's oscillating in the y plane, or the y direction. It says the wavelength, we can write this down, the wavelength is 10.6 micrometers in the infrared. And the electric field is parallel to the z-axis with Emax being equal to 1.5 megavolts per meter. We want to write vector equations for E and B as a function of time and position. So we're only given two pieces of information right here. And we had from before that the general form of, we'll just pull one of these down here, the general form of one of our waves looks like this. We also know a couple other things. We're going to need this equation. We're going to need these equations. And we're going to need these equations. I think we need both of these. So we'll need all of this stuff. Make it a little bit smaller. Okay, so we want to write, basically, the electric and magnetic field as a function of time here. So let's start off with the electric fields. So the electric field is going to be given by, it is oscillating the electric field's actually oscillating in the z direction now, right? So we're going to have to put a k hat in here, right? And this is going to be multiplied by the cosine, We're going to have to put k hat multiplied by Emax, which we know, multiplied by the cosine of kx minus omega t, which we don't know. So we're going to need to calculate k, omega, we have Emax, right? So for k, we can calculate it using that equation. So k is going to be equal to 2 pi divided by the wavelength, which is 10.6 times 10 to the negative 6 meters. Let's calculate what this is. This is going to give us our wave number k. So I got 592,753, so about
Me as well.
so it's 5.93 times 10 to the 5. You could put meters inverse here. I'm going to put radians per meter. Okay, we got the value of k. We'd also like to find omega. So how are we going to find omega?
The fact that c equals k over omega.
Yep, so we use omega is equal to c times k from this equation right here.
Or omega over k. What am I doing?
Mm-hmm.
I said c equals k over omega. It's the inverse of that.
That's okay. For c, we put the speed of light, which is about 3 times 10 to the 8 meters per second. You can use a more exact number for the speed of light, but I'm pretty much always just going to use this because it's like the speed of light is something like 299 or 297 something. It's very close to 3 times 10 to the 8, or 300 million meters per second. It's extremely fast. All right. So there we go. We've got omega. Oh, omega is equal to c times k. K is this number that we just calculated. So 5.93 times 10 to the 5 radians per meter. The meters will cancel out, and we'll get a unit of radians per second. So what we get is, anytime we're talking about frequencies, the number is always going to be very high when we're talking about light waves. The frequency is a very large number usually. In this case, it's 1.8 times 10 to the 14. That's pretty close to visible light, but I think it said it was an infrared laser. Okay, you guys agree with that? 1.8 times 10 to the 14?
Yeah.
So I think we can now write down what the electric field is up to a negative sign at least. This is going to be k hat times E max, which was given as 1.5 megavolts per meter. We'll just put that in here. Cosine of kx, so k is that. Minus omega t. Let me just make some extra space here so that we can put like bracket, parenthesis. So that's all times x, and then omega was 1.8 times 10 to the 14 radians per second times t. And there we go. That should be our electric field as a function of time for this wave. You have any questions? We want to find the vector equations for E and B as a function of time and position. So if we want to get the magnetic fields, we're going to need the magnetic fields is going to be equal to, so the magnetic field's oscillating in the y direction, right? So we're going to need to put a j hat in here. And we're now going to need to know what the maximum value of the magnetic field is, but the rest of the equation is going to be exactly the same, because the idea is here that the waves are basically in phase with each other. The magnetic and electric waves are in phase with each other. Okay, really, that happened? Okay, I want to do this, copy, and then just want to click, there we go. They're in phase with each other, so if they weren't, you could have some kind of phase constant over here that were different between the two of them, but in this particular case, because it's a laser, they're going to be in phase, and I think most of the homework problems you guys are going to see, they're going to be in phase. All right, how do I find the maximum value of the magnetic field?
E is equal to E max over B max.
Yep. So that means that B max has to be equal to the E max, which was 1.5 megavolts per meter, divided by 3 times 10 to the 8 meters per second. And in case it's not clear, mega is million, so this is 1.5 times 10 to the 6th volts per meter, divided by 3 times 10 to the 8 meters per second. So we end up getting that B max is... See, the theory for this chapter is really hard, but I think that the problems you're going to find are pretty easy, because it mostly involves just applying these pretty simple formulas. So I got 0.005. This is going to be Tesla, because it's going to end up being volt seconds. Is that right? It looks like you get volt seconds out of here. Am I wrong?
Meters cancel. Yeah, volt seconds.
Did I do that? Did I write that down wrong? No, this is right. Yeah, E over B should be a velocity, so that's right. So then E over C should somehow be magnetic fields. I would think it would be volt seconds, but you'd need like a meter squared. These do cancel. No, they don't cancel.
Oh, they don't get meters
Okay.
squared in the denominator.
Yeah, that's good. That's a Tesla. Yeah, that works. Okay. Because if you look at like Faraday's law basically says that a volt is equal to flux, which is Tesla times meters squared divided by seconds, right? Because it's EMF is equal to ddt of flux. And if you rearrange this, you'll get volt seconds divided by meters squared equals a Tesla. So this is a Tesla. Okay. So that's going to show up right here. That's our B max, right? So 0.005 Tesla shows up in the front. And what's the final thing we need to do to make sure these two equations are correct? We need it to travel to the left, right? Not the right. So we can check for the direction
By crossing.
by crossing the vectors, yeah. The direction of propagation has to be given by E cross B. So in this case, E cross B is going to be K cross J, I think, which is negative X. That's fine. So we're good. So in this case, that's K cross J, which is negative I hat, because you're out of order, because you're going backwards in the alphabet. If it was J into K, it would be positive, but we're going K into J, which is negative. There we go. Those are the electric and magnetic fields of a laser beam. Anyone have any questions? All right, then we will take a break until 3:10, and when we come back, we'll talk about the transfer of energy and power in electromagnetic waves. So break.